Okay, so this mini lecture is going to look at the motion of an object in a little bit different way. We've talked about objects moving in one or two-dimensional motion, and we've talked about how objects change their motion as a result of a force. We've talked about objects moving in a circle. But what about an object that's rotating? Now let's take this object that we've modeled as a dot, like this eraser. We just talked about it as an eraser moving in a plane and being caused to change its motion by a force. But what about rotating the eraser? What about rotating an object that now has dimension, that's beyond just a model of a single dot, like in our free body diagrams? How do we get an object to rotate? So that's what today's mini lecture is going to be about. How do we rotate an object? So if we think about what it takes to rotate an object, we're going to find that there are two things that are important. The first is that we can rotate an object about a variety of different points. I could rotate the object about this eraser about the end of the object, or I could rotate it about the middle of the object. I could rotate it in multiple directions. Okay? I could rotate it along this axis, or along this axis, or along this axis. Okay? So rotation is a much more complicated thing to be thinking about because we have more things to think about. So let's just talk about rotating an object in a single axis, in a single plane. And I'm going to actually use this plane, kind of the vertical plane, in your perspective so that you can visualize the rotation. So like I said, we have to decide about which point we're going to rotate the object. And we call that a pivot point. So when we think about rotation, one of the first things we have to think about is what we call the pivot point. And we're going to find in our analysis that that pivot point isn't always where the object actually pivots from. It helps us with an analysis. But when we think about rotation conceptually, let's talk about it just being how the object is rotating about. So if I set my pivot point here at the end of the eraser, how do I get this object to rotate? Well, I need to apply a force. So applying a force will help me to get that object to rotate. But let's think about very carefully what that force might look like. If I want to rotate the object about this pivot point, and I apply a force at the pivot point, pushing on it, I can't get it to rotate. So the first thing we recognize is that the force has to be applied not at the pivot point or away from the pivot point. And I'm going to abbreviate that PP. All right. So if I apply a force here at the pivot point, I don't see any rotation. But if I apply a force out here at the pivot point, I do see a rotation. So the first thing that we have to know is that the force is applied away from the pivot point. Now that distance away from the pivot point we call the radius. Why might it be called a radius? Well, let's imagine my my eraser, and here's the pivot point. If I am going to apply a force away from the pivot point, let's say here at the end, like I demonstrated, and I keep applying that force, eventually this eraser is going to move along in a circle. The radius of that circle is going to be the distance between the pivot point and where the force is applied. And that's what this radius is defined as. The distance between the pivot point and where the force is applied. Okay, so the first thing that's going to be important in being able to rotate an an object, is to apply a force at a distance, a radius, away from a pivot point. Okay, but is that all? So let's look at that eraser. If I apply a force at a distance away from the pivot point, I get a rotation. But what if I apply a force like this? I'm at a distance away from the pivot point, but am I rotating the object? So what does that tell me? What what's different about this force that I'm applying and this force that I'm applying? Well, this force, if I draw it on my diagram, that force looks like that. The radius is parallel to that force. They're in the same line. Whereas in the case that did cause the rotation, the radius is perpendicular to the force. And that's our second key feature, that this force is perpendicular to the radius. Now, what if I apply a force at an angle? Will that force generate a rotation? Well, let's see. So here's my eraser, and I'm going to apply a force in this direction. Sure enough, I get a rotation. But that force isn't perpendicular. What do we know about vectors? Well, there is a perpendicular component. And there is a parallel component. Do you think the parallel component's doing anything? Nope. Just like this force here in blue is not doing anything. But the perpendicular component is. So we're going to modify this idea. The force has to be perpendicular to the radius, but all it needs, oops, oh, I spelled that wrong, is a perpendicular component. So if I have a force applied at a radius, and that force has a perpendicular component, I will get an object to rotate. Well, this idea of rotation, what causes an object to rotate related to both the radius and the force, is called a torque. So a torque is the force at a radius that causes an object to rotate. We represent torque by this lowercase tau. So this symbol is a lowercase tau, and that's how we traditionally represent the torque. All right, well, let's dive a little bit deeper into the relationship for torque based on these two ideas. And we're going to do some thought experiments. I don't have a way to demonstrate here in the Learning Lab very well because of the way it videotapes. So let's think about how torque might be influenced. How easy is it to get this object to rotate if I apply a force with a perpendicular component? And we'll use the example that I have above first. If I apply a force like the orange force, and I'm going to extend its length so that it matches the magnitude of my yellow force here. Which of these two forces, A or B, is going to be most effective? Is it A or is it B? I want you to think about when you try to open a jar. Like imagine that you want some peanut butter or jelly. Jelly's a good one because the jar gets all sticky and gooey and it's hard to open. So you're trying to open the jar and you kind of can't get it open and you're struggling to get it open. So what do you do naturally to open the jar? Well, you kind of start to contort your body, reposition yourself to make the jar open easier. You're still applying that same force, that same magnitude, but you are repositioning yourself. You kind of curl around it and try to crank on that jar, repositioning yourself to make rotating that lid easier. So, what are you doing? Which is more effective? The original attempt at opening the jar or repositioning yourself to be more perpendicular? The more perpendicular the force, the larger the torque, the better the torque. Now, you also might increase the torque. If I can't get this jar open, and my 15-year-old son is in the room, I hand it to him first. Say, Zach, open this jar. You're stronger than I am. He might be able to open it right away. So I don't only position my body for that perpendicular force, but if I could exert a larger force, then I might increase my torque. And that's the relationship between torque and force. If I increase the force, and particularly the perpendicular component of that force, then I increase the torque. So a proportional relationship. I can either make it more perpendicular or I can get a bigger force, which subsequently will give me a larger perpendicular component. All right, so we know that the torque is directly proportional to the force perpendicular acting on that object. What about the radius? Let's imagine that we apply a force to the eraser at this location A or at this location B. Now these are the same forces, but our radii are different. I have a smaller radius in B than I do in A, which is going to be easier to rotate the object. So now I want you to imagine you're trying to loosen a bolt on your car, let's say, on the wheel. And you're like trying to rotate it, you get perpendicular, you try to rotate, you just can't loosen that bolt. You can't rotate that bolt. So what do? You go grab a cheater bar. You stick it on the end of that bolt loosener wrench. You stick it on the end of that wrench, and you apply a force at a larger distance. Same perpendicular force, but now at a larger distance. And you get that bolt to rotate. Which is going to be more effective, A or B? A is more effective. If I push down on the eraser at the point A, I can rotate it pretty much. But if I push down at B, it takes a little bit more for me to rotate. If I increase the radius, I increase the torque. It becomes easier to rotate. I get a bigger torque if I increase the radius. Well, this relationship leads to exactly what torque is. Torque is equal to the force perpendicular times the radius. That's what torque's all about. Now, the official mathematical relationship for torque is a cross product. Okay, so we got to think back to our calculus days in terms of the cross product. Force cross R. Now, this cross product tells us something, gets us to a relationship that we are going to think about forces in. And we're not going to do the cross product in the old-fashioned way, but what we are going to define the torque as and then mathematically use this relationship. The torque is going to be our force times the sine of an angle, we'll talk about what that angle is, times the radius. And it doesn't matter how we write that, we might write it in this way as well. So the force times the radius times the sine of the angle. What angle are we referring to? This is the angle between the force and the radius. One too many loops there. The force and the radius. The angle between the force and the radius. Now, torque, because it's a cross product, is a vector. All right, so torque is a vector. And vector has always been a direction-dependent element. Vectors have always been direction-dependent. We've always talked about direction as right or left. Well, when we're dealing with rotation, it's a little bit different. We don't really deal with rights or lefts in rotation. So what is the direction of the torque in terms of the rotation? I'm just going to give myself a little bit of space, a little bit of erasing here, so that we can write these notes down for you as well. All right, so the rotation defines our direction. If I rotate the object in a counterclockwise fashion, so rotating counterclockwise, Well, when we talked about angles in our angle analysis stuff, those are positive angles, right? Going from the positive x-axis in that direction. Positive angles. Counterclockwise exerts a positive torque. And if we do our angle correctly between the force and the radius, that will tell us that. It'll come out as a positive angle. And we're going to do analysis with torque and get into that. We're not going to talk about it right now with the conceptual ideas. But we will exhaust that idea. Well, likewise, if I go in the opposite direction, clockwise direction, like a clock, well, we know those are negative angles. Clockwise rotation gives me a negative torque. All right, so if I'm going to rotate this eraser, I'm going to flip it around just to make it look a little different than the ones we've been talking about. If I apply a force in this direction and rotate the eraser in this clockwise direction, I've exerted a negative torque. If I rotate the eraser in the counterclockwise direction, I exert a positive torque. Okay, so that's our general introduction to torques. We're going to start talking about how we analyze the torque acting on an object and what process we go through to do that. And then we're going to move into what I think is a really, really fun idea, which is analyzing static equilibrium. So how do we look at the forces of an object that's not rotating or not moving, and how can we analyze the forces interacting with that? All right, conceptual ideas about torque. Good job.